Speaking of OpenCV, I'd like to invite Gary Bradski to the stage. For those of you who don't know, he's the founder of just one of the most popular open source computer vision libraries, OpenCV. I'll let him tell you everything he's done between then and now, except that a year and a half ago he sold Industrial Perception, a robotics startup that he co-founded, to Google. And he now runs the west coast of Magic Leap, a startup that at least a few of you have probably heard of, in augmented reality. So Gary's going to give an insider's perspective on the new version of OpenCV, how developers can utilize it to maximum advantage, and offer a sneak peek into future plans for OpenCV. Thanks, Gary.
Okay. Security alert. Uh-oh, viruses.
And is infecting our computer.
Yeah, I actually edited this in China, so, you know, whatever. Might have happened. Let's see. Okay, so I started OpenCV back in Intel when I was wandering around. As actually, you know, they wanted me to write papers to put the new Intel research labs on the, you know, make its mark and start getting publications. I thought, you know, academic places are pretty good at publication, and maybe Intel should be doing something else. I did a tour around the country. I saw that Media Lab sort of papers were at a higher level, mostly because the students would start from their infrastructure they found there. And a lot of the other places were reinventing the wheel over and over, like, and so I thought, you know, Intel at the time wanted to generate a demand for more MIPS out in the world. Computers were fast enough to run spreadsheets and word processors. And I thought, well, if we accelerate these sort of new sensing capabilities, that will fulfill all these things, and that would be better for Intel to spend its time on than publications, of which, you know, I did maybe 70, 80 there anyhow. So I launched OpenCV, and it's one of the few, you know, I did it to help accelerate computer vision. It's one of those few times where what you planned actually happens. So, overview of OpenCV. What it is, probably all of you here already know. But, you know, again, it's a free and open computer vision library meant to accelerate visual intelligence out in the world. So computer vision out in the world. It's got a BSD license. I sort of like Apache better now, but it didn't exist then. Too late to change. But this is still easy for business or any other use. It was intended to be used. And the size has grown a lot, though we now made it very modular. Last time I counted, this is from SourceForge, these are people who grabbed the binaries and whatever, was 13 million downloads, but that's not half of them, you know, because OpenCV is distributed on Debians. Git doesn't make a good way to track statistics, so, you know, people are downloading there, I have no idea how many. But, you know, I typically grab from Git and build, I don't take from SourceForge. So the Git statistics, we now have a lot of people contributing. You know, 4,000 patches, and so just the library itself now has a HAL layer. I'll talk about hardware acceleration layer. There's a hardware abstraction layer too, so we're going to have both types of HALs. But SSE, Neon, Intel performance primitives, and so it has a parallel forward, it has a bunch of accelerations. We're going to talk about how that's going to get more dominant. And 3.0 has come out. Below is the OSs that are supported on the build bots, which, you know, run all the time. So basically all the major ones: Windows, Linux, Macintosh, iOS, and Android. These are the statistics. I grabbed this a couple of weeks ago. This is all from SourceForge. So, you know, this can continue rise in downloads. The sort of downloads per month is nearing 300,000. So when you consider this, it's a vision library. You know, it's not Linux. It's not Harry Potter, so it's pretty good. The dominant OS is Windows, but that's a little bit skewed because a lot of people in the US, I think, use Linux more. I think that's coming from China where they use Windows a lot. And people get OpenCV from Debian's and whatever, or GitHub here more. And so the usage statistics is China is the biggest source of downloads. When I go there, I'm like a rock star. It's like being a rock star on Mars, but for me. but I think that's skewed in that that's just they're getting it more from SourceForge. Other countries get it from other sources. So what does it cover? Basically it's a wide look at computer vision. So image processing and many of these things are going to survive deep nets, which we also have now. But there's basic image processing, computational photography, image transforms, geometric stuff, fitting, optical flow. So there are many different techniques, and we're accelerating the more of dense flow, and it's a current project to really get this optimized. Segmentation, calibration, we're putting a lot of effort on improving that now. Features, 2D, we've been involved in SLAM and Deep SLAM, and so far the geometric stuff is just there. I think there's going to be some sort of merging of deep and also traditional things. I'm thinking robotics too. Kinematics, they really work. It's not been invented, so why do you want to learn something that is actually a physics item? You probably just want to tune it, right? So a lot of these things are, what deep nets will do relocalization really well, but exact, when you really want to hold something still in a scene and put things there, you tend to use geometry. So I think a blending of these things will work best in many situations. Again, we have this DNN that we're working on. It's just intended to read libraries from wherever and run them. I think in the TensorFlow talk, they're mentioning automatic compressing to 8-bit. You've thought about this a bunch, and it turns out it might be better to do some layers more, some layers less. But that it's great for classification, but not necessarily if you're going to do something regression. That just compressing the net is probably not going to give you your 1%. But for classification, maybe. So we might put more tools around that. Sometimes it's important that 1%. If you're doing pedestrian detection, you don't want to miss 1% of the pedestrians if you're driving. That means you will kill someone all the time. But so computational photography, there's a lot of cool stuff people are doing, with that. Anyhow, some real world uses. I led the vision team for Stanley, which is now, I guess you'd call it the grandfather of the Google robot. So first Stanley went in and became Street View, but Street View was just a cover for Google doing Google Maps. So we're just taking pictures of the world where we know where we are. Isn't that? Because I think they were using TomTom or something at the time, and they knew they had to replace that. And so it became sort of the forerunner of developing the Google Maps and Street View. But also, that and the next DARPA challenge became the Google robot. A lot of the team is still there. Ironically, Google moved their building like 3 blocks, so every day I have to run into these robots that I help grandfather, and then I just praying that they know what a bike is and no one made a bug somewhere. So I ride right by the building every day and run into robots. Well, hopefully not physically every day. This is another thing that we did that was mentioned, industrial perception. So I spun out of Willow Garage with Ethan here, who I'll talk about in a second, later on in the talk. But this is going very slow. Trust me, the robot was much faster. So you see, it's throwing boxes. It didn't really throw boxes. It placed them on a conveyor belt. But for Larry Page's birthday party, this is what happens when you're a multi-billionaire. You get to have a company throw party favors for you. and which might have actually resulted in the sale of our company because he likes party favors, I guess. So Google bought this company 2 years ago, 3 years ago now, I guess, and so they're still doing mystical things inside there. But we were looking around for what robots should do, and manufacturing is a big thing they should do. But we noticed in distribution there was no robots unless you count switching conveyor belts as a robot. And so we thought, well, why not be the only one on the block there rather than there are dumb sort of robots all over manufacturing. But that's what was done there. Okay, where else is OpenCV used? Just everywhere. I've got people from Iran, come to my conference. We're using it, in gold mining or uranium extraction. Who knows? And someone, tell me that the Russian military is using it, and I was so happy about that. But I've had people in China say, oh, they're using it, in mine safety, so they have monitoring cameras, and there's a swimming pool drowning detection in Europe, so I've seen this thing save a whole bunch of lives of mostly people having heart attacks sinking in the pool, but it detects them. So my little part of some algorithm, helped that out, and on and on. SLAM, machine vision. I have a friend with a LabSite. That LabSite is this microfluidics company. They really can do what the Theranos. They really can do any test on a drop of blood, but they're a real company rather than a hype company. They're profitable and pretty big in microfluidics, but they use OpenCV in their automatic robot that does the cooking of the trays once you distribute this stuff. They use ultrasound to move droplets around. Anyhow, robotic bin picking, computational photography, I've been all through this. Okay, funding, who's involved? Intel, Google, Magic Leap, ITSEs, and Willow have been the biggest contributor. Intel and Google are consistent contributors. I'd say OpenCV sort of runs through 200K a year, something like that. Vadim Pizarevsky is the lead developer, has been there with me forever. I was the one who started it. ITSEs, Yuri comes from that company, has been the help. It's sort of evolved out of and with OpenCV and have helped maintain it all along. Couldn't do it without them. I've been the director. We have weekly meetings. You're welcome to join if you want to chime in and take some role. Ethan Rubley is now going to be CEO of OpenCV.ai, which I'll talk about in a second, and many others. Community's getting big, since 3.0 released in June, there's been, over 500 pull requests of new functionality. So what's new in OpenCV? OpenCV 3.0 came out recently. It was an effort to bring up to better C++ standards and to make things more modular, and because maintenance was getting to be too much of a burden with C code and all these other things and wrap C code. So now this is purely C++ functionality, and the standard C is sort of deprecated. To do this, we've actually shrunk or tried to shrink the core of OpenCV, the core algorithms, to a smaller subset, and that's what you get when you download OpenCV. You must now also download OpenCV Contrib. That's this larger circle around everything. What it is this keeps up with the state-of-the-art in Vision, which evolves so fast now that we just can't keep it in the library. But we essentially took sort of Google-style coding standards, unit tests, and whatever, and we've applied that to all of OpenCV and to Contrib. So to contribute, you have to have unit tests, you have the style guide, you have to pass the build bots, and then it becomes you can contribute it and it becomes a sort of self-standing module. If you're a company, you can just build a self-standing module out of the same technique. That doesn't have to be public, but it's a very nice sort of modular way. I've used it to sort of teach students better coding practices that are maintainable. And so it sits there, and you can sort of pick and choose between, I think there's now 31 different and mostly higher level functionality there. So here's some of the stuff that's in it. I don't know how long I'll let these There's 3D viewers, so there's a 3D module, there's fast normal finding, there's fast planar segmentation. This is Malik's finding human-like lines in an image. The kind of things, probably do this by a deep net, but he did this work before. Line segment detection's really nice. This is computational photography, blending, again, compositional. I don't know if all these effects come out so well, but stylization of image, Python tutorials. I think this video gets a little bit more boring here. Text detection. So text detection has gotten better and better. I'm skipping on. This is 2014. These all come from Google Summer of Code, which we actively run. We might start doing OpenCV.ai Summer of Code then. So text detection has now gotten text reading, and this is again being improved, but with deep nets this year. So just a useful functionality that's sort of built in. Python has gotten better and better, so we have full Python interface and a Java interface now. There's still, people use a lot of this feature detection, especially with Ethan and whatever we developed Orb, just at that point it was to get the world off of SIFT, and that worked. And now I think it's probably the most used in mobile. People use it everywhere because it's such a lightweight detector. Even though it might not be as robust as some of these other techniques, it's just it's very lightweight, so people use it. Let's see how long I'll let this video run, so don't run out of time. Okay, all this sort of separating light, color transfer algorithms. This is computational photography stuff again, which is a fairly big area. It's all in Contrib, color constancy algorithms, gray world algorithms. So these are all in Contrib. And Contrib has docs, it has tutorials. This is custom calibration patterns. You can just show it any picture and transfer measurements from a known calibration grid to that picture. It's sort of for robotics, so you don't always have to use something ugly for the robot. You can just use an Ansel Adams picture and it becomes your calibration pattern. At one point, we were trying to embed hidden sort of barcodes in there. We never spent enough time on it. Someone should pick that up so that you can put barcodes and it looks like a picture. Looks just for beauty. Okay, denoising. I think I better move on, or there's too much of this. 2015, more and more, and there'll be a 2016. 2015 was augmented reality, these Aruco patterns, and support for really knowing where the camera is. Deep nets came in, and so we have a bunch of deep net functionality, sort of having a model zoo. This is the Googly Net or at AlexNet, I'm not sure which one. but this is in there as an example. Again, we're not really focusing on learning, but just ingesting networks trained anywhere. This is tracking algorithms. We continue to work on. These have evolved into being pretty robust face detectors that are much more robust than the original one, sort of picking up every face in the image. This is the tracker again. So this is just sort of a tour of functionality, some geometric and computational algorithms that are hidden in there. There's optimization algorithms. I think I might move on soon. So these videos are on YouTube. You can look them up, Google Summer of Code, OpenCV, Google Summer of Code. It just sort of gives an overview of the functionality. This is, better stereo, so there's, more robust stereo algorithms, structured light stuff for structured light capture is in there. I have a projection algorithm there. I wanted people to use this to, project over surfaces. So this is projective vision, where you can make a surface look like something else, just doing that for fun. There's a big arts community that uses this, and I wanted to support them more. We haven't focused enough. This is sort of planoptic imaging and reconstruction, on and on. Okay, I'm just going to move on. So, bunch of functionality. Now what else are we doing? And I'll get more into this. There's now a HAL layer, which is hardware acceleration, and it tried to make it transparent. So just like, which I think I showed 2 slides from here, the ACV library, but more and more functionality where you drop it in, there, you make no changes. Like if you have a GPU, the code doesn't change, it just uses it. That's what we want to do, and these are parts of these efforts showing speed up. Obviously, some things speed up well on different hardware, and some things don't. But overall, Intel Performance Primitives and GPU, certain classes of core functions speed up very well, and so they're there. This was Kronos, which sort of OpenCV was one of the generators of, and Victor, who was CEO of ITSE's and now CEO of ITSE's 3D, he went to these meetings. And so there is an accepted, sort of hardware acceleration layer. Most people are now just running beyond this and not really claiming to adhere, but they do adhere to this. Probably ACV does adhere, but it's just run beyond because the committee moves pretty slowly. This is ACV. I got this from Victor, I think. And basically, right now it's a different namespace, but as soon as they drop it into the acceleration layer, if you have it, you accelerate. And the sort of overall effectiveness is shown on your right. Basically, if you've done optimization, you have the experience of really, working hard and optimizing something and not having it make any difference in the actual, overall end-to-end performance. But here, there's some examples of robotics and car getting 1.5 to 2 times acceleration, which is quite good for overall algorithm. It means the important functions are really getting accelerated. Oh no, I got 9 minutes here. Okay, so we did this Aruko patterns. I created this Charuko calibration board. This is just some highlights. Camera arrays and things are getting complicated, so you really wanted a better calibration pattern where every corner has its label, so you don't have to see them all. I'm going to accelerate deep neural networks. I already mentioned that we read them. This is showing things recognized. Yay. I'm going to move on. So a bunch of things, examples. People are using this in mobile drones and text. And okay, I'm going to move on to this. So where's OpenCV really going now? We've noticed that embedded is getting big and cheap, or Raspberry Pis and whatever. So you have all this compute and cheap cameras. And so we decided, because I'm tired of begging money from these corporations, just make a for-profit out of OpenCV that'll support in the same way ITSE's 3D does. The OpenCV stays open and free with better support. We're trying to put a revenue stream behind this. And what we thought, this is where our starting point was smart cameras. So embedded focus. And so, what we're going to try to do is make a platform, trying to jury-rig it into the platform that you just won't do embedded vision without this anymore. That's the goal. And this will be an open and free spec. But what we're going to do, so it basically has timing, synchronization layers, and makes a real solid commercial package where you get rid of these complaints. So like, oh, you work on a PC and it doesn't have the same performance, something changes or something slows down. No more. So we're going to work closely we're going to have OpenCV certified hardware, and that means it works, right? And if something doesn't work, you have a big red flags there. Say, don't try optical flow on this, it goes slow, right? And so we're starting to partner, and we invite partnering with hardware makers. So we're going to have this platform, and this thing will replicate in a PC, in the cloud, and hopefully be a uniform experience. But on the hardware, it'll be tightly coupled. So what are we doing with it? We're going to focus on light fields, and that's going to be the proprietary area of OpenCV. But of course, making this available for simple licensing, cheap. And we're going to build on this itself. We're not trying to make a lot of money. We're just trying to support this platform and thing with some licensing fees, but meant to sell, like the goal of OpenCV, accelerate vision. So this is now putting enough support where it keeps this thing really solid. So light fields, if you don't know what they are what you see here. Cameras are not a light field, they're a pinhole prick at a light field, one ray of light's coming in. And then they had to invent lenses because there's not enough light coming into a pinhole. So this is just going in the opposite direction. The camera is now what? It's a software device. So your lens is a software creation, not a physical creation. The hardware is a sampling of the light field. If you don't sample enough, you won't be able to implement your lens. But if you do, you'll be able to implement any kind of imaging you want. And that's where we're heading. Okay. Light fields, as I said, turn it into a software object. You get all kinds of stuff, depth, normals, separation. I try to show on here, you can see through trees and whatever. Why? Because here I have an occluder, but if I move around, it's not so occluding. Well, the light fields has a spatial extent. Now, there are light field cameras out there, of course, but we're doing this in a different way. We're not putting the plenoptics on the imager, forcing us to invent a new imager. We're letting the whole world invent and keep those cheap imagers going. We're putting this in grids of cameras or in grids of lenses. So there's a whole bunch of things you can do with light fields. I guess I'm running out of time a little bit. Deblurring, a closed form solution for SLAM and high dynamic range. Light fields capture rays, cameras captured pixels. Light fields turn rays into pixels by software. So, what we're going to do is have a real tool chain for light fields that makes it easy for someone to develop with them. What they can be used for, light fields are just a no-brainer for drones. I think once these get out there, you just won't use any kind of camera. Automotive, everything, robot manipulation, deep nets, they just make a lot of sense. The problem is they haven't been available in a nice way, and so we aim to change that and in a cheap way and an effective way. So we're partnering and whatever. We're time, still says 4 minutes. Basically, we're going to do this within 6 months, come out with the first development boards and partner, and hopefully hardware and software. This is getting, so you'll see more of that. This is just the resource page. I'm also going to plug the book. It's OpenCV 3.0 has just gone into production, and so that means it's going to come back to us for final edits. It's going to go out, and by summer, it'll be out on the market. I was just going to go through, why we do this. Maybe I'll skip that and go on to questions.
That's why there was a difference between your timer and my timer, because I wanted to allow time for questions. So microphones on either aisle, please queue up. We got time for just a couple of questions. And I'm going to show you how generous I am. I'm going to give you the chance via my question to talk about something that you didn't have time to talk about. Gary and I hung out for a while last night at a party. And I said, Gary, everything in OpenCV is classical computer vision algorithms. Deep learning is the hot new thing. What are you doing about deep learning? And he had an answer for me. Well, so give me the answer. And if you could also tell him your thoughts on how classical and deep learning-based computer vision will interrelationship in the future.
Well, I think I covered that a little bit, but we have DNN. It's in, deep neural networks in OpenCV Contrib already. And so one of the ways is just to ingest deep nets learned by any other net, TensorFlow, basically a converter back and forth to any of these algorithms. And just to be able to ingest that in embedded. Now, in the OpenCV.ai, we will, be partnered with that hardware manufacturer to maximize the runtime speed of that. But I think I mentioned that, for example, in robot kinematics, this is real physics, and what are you actually going to relearn that from scratch? It's sort of silly in a way. Wouldn't it be better to have, just since it is just gradients anyhow, to tune it within a gradient framework? So I think, to an extent, there'll be a blending of this. So far, I haven't seen the real geometric algorithms, now maybe someone contradict me, please, have really worked solidly. Like when I need to regress solidly to a position in space to, let's say, millimeter accuracy. I haven't seen that, but I have seen that it gets you close. And now we can do a geometric refinement. So I think there'll be a natural blending of algorithms in this way, especially where it makes sense. Now, for pure classification, no. But I think there'll also be, advantages. The light fields have a lot of information, and they'll play well with deep networks. If we express them in the right data structures, I think it's just a natural. Don't know.
Scared.
Yeah.
Jesse from ARM Research.
Yeah.
I have a question about the light field data format. So the kind of the mats that are currently in there for image, that's just very array shaped, is very local and friendly access pattern. What does it look like for the light fields?
So we're developing these, but a light field is kind of a registered stack of image. So a lot of it is just a stack of images where the sort of indexing makes geometric sense, that you're able to address groups of related pixels. I mean, basically to reassemble the array. So it will look like a tensor. It will be a modified version of mat or a stack of mats, but it's really the meaning of the pixels in there. Now also, the data from light fields is much larger, but it is very redundant, and so it's very compressible too. So that will be involved too. I don't know if I answered, like this is not out as a published spec. We're in fact working on it right now.
And thank you.
Yeah.
Okay. You're free to go. Longstanding friend of the Open Division Alliance. Thanks,
Yeah.
Gary.
Great.